Yes. Very good evening, dear participants. We welcome you all to this webinar session. We welcome you all to this Trends in Aeronautical Engineering. Today's webinar will be on Advances in Aerospace Materials and Structures on behalf of Department of Aeronautical Engineering of JEPPIAAR Engineering College. I would like to first thank our director, Dr. M. Rachna JEPPIAAR, and our principal, Dr. V. Natarajan, for supporting us to conduct this webinar session. And on behalf of my head of department, Dr. D. Thanigvel Murugan, I once again welcome all the participants and also welcome today's guest, Mr. Daniel Paul. It's nice to have you, Daniel, today with us. Thank you for accepting our invitation and coming forward to give this webinar session to us. Today's webinar will be interesting, especially for undergraduate aeronautical engineers and postgraduate aeronautical engineers. So Daniel Paul is an alumni of JEPPIAAR Engineering College. He was one of the best students we ever had. He is a recipient of silver medal in Anna University during his undergraduation, and he was blessed to have this PhD, integrated PhD program at IIT Madras, and also is blessed with stipend. And now he has completed his PhD, and due to this lockdown, still there is just one hurdle he has to go, and he has 3 journal publications against his name. He has done 2 best performances in international conferences, and he's so studious. His interests are reading books. He keeps engaged in all spiritual activities, also sporting activities. Uh, Apart from this, he is one of the obedient students we ever had, and so sincere, so dedicated, very helpful. And I hope all the students today will definitely make use of this webinar. And today's session will be on structures, specifically for the students in final year. I will request you to pay attention and take more from this. During the webinar, you can post your queries or your questions in the live chat, and they will be answered at the end of the session. So welcome, Daniel, and kindly take over the session.
Thank you, Professor Heston, for the kind words. And yeah, it was indeed a great privilege to study at JPR under Professor Heston, the current HOD, Professor Thanigvel also. They all have taught me in my UG, and I'm very glad that I could give back to the college and that I could share the experiences that I had during my direct PhD program at IIT Madras. So now we'll go to the presentation. Yeah. So is it on the screen, sir?
Yes, Dan. Yes, it is. It is there.
Okay.
You can go ahead.
Yeah. So I welcome all of you. Thank you for taking your time. And today I would like to share a bit about the advances in aerospace materials and structures from a researcher's point of view. So it's not going to be a lot of technical stuff. It's going to be a lot of experience, my experience, which I went through during my PhD, and especially to inculcate an interest in research. So as Sir has already introduced, I'm Daniel Paul, a research scholar at the Department of Aerospace Engineering in IIT Madras. And the aim of my talk, the aim of this webinar today will be to provide a brief introduction to aerospace materials and structures. It will be very brief. Many of you might already be knowing about these materials and structures used in aerospace and other applications. And the second part is mainly to take you through the process of a research scholar's work. That is, how to approach research and what are the steps in research that are very important. And it'll be good if undergraduate students or postgraduate students inculcate that now itself. Okay? And the third thing is to encourage students to take up research as an interest. It may not be as an academic career or anything, but as an interest, how to take up research in day-to-day, in the daily studies itself. So as we know, even yesterday there was a webinar on shock tubes. So aerospace engineering has several disciplines under it, and three are very major: aerodynamics, structures, and propulsion. So aerodynamics, as you know, deals with the forces on the aircraft when it is in flight. It can be an aircraft, a spacecraft, or any flying object. Structures deals with the structural design, and what keeps the structure together. And propulsion is deals with what powers the aircraft or the spacecraft or space shuttle, or it can be any flying object. What is that thrust providing device? And there are other sections of aerospace engineering, such as avionics, but that comes more towards the electronic section. So aerodynamic, structures, and propulsion are the three major pillars of aerospace engineering. So today we'll be seeing about structures, and in structures there are two main classification or two main divisions. One is material science, and the other is structural analysis. So in material science, we deal directly with the material itself. So if it is a metal, we deal with the structure of the metal. We deal with what are the constituents. If it's an alloy, we deal with what are the constituents of the alloy and how they react with each other. And there are different scales to it. So we can look at it at a macro scale. So a macro scale is nothing but how we see objects to the naked eye. So we can analyze these materials in a macro scale. It can be in a micro scale, nano scale, all the way down to atomistic scales and atomistic models of different materials. And the other is structural analysis. So in structural analysis, it deals with the design of the structure, how things are joined together, and what are the shapes which are used in the different load carrying members. So structural analysis can be either through conducting experiments, it can be through analytical models, and it can also, in recent years, a lot of research is being done on numerical simulations. So we need not actually make a structure and test it physically, but we can run numerical simulations which tell us which is the best possible configuration and which is the optimized structure. Now coming to materials. So in general, when we see any product, the first thing that we look for is the material. So for example, if we buy a mobile phone or a laptop or any other device, the first thing that we see is what is the material. Is it made of some cheap plastic material, or is it made of some very good material which can withstand stresses if it's dropped? And we see the glass, whether it has some extra coatings to protect the material, protect the product. So materials define the product. So if we take a product, the first thing that we see is the material which it is made out of. And the second thing about materials is that materials dictate the cost. So you cannot have a very high performance material at a very low cost. So depending on what is the expected cost, the materials are decided in different structures. So that is an important parameter. But this cannot be done at the expense of safety. So safety is primary, especially in the aerospace industry. Safety is one of the most important parameters, not only in aerospace, in everything, but more in aerospace. Because when an aircraft or a spacecraft is flying, and if something happens because of the material, some material erodes or some damage happens, it can be catastrophic and fatal, completely fatal. So safety depends completely on the materials and design of the structure. So materials need to be chosen very carefully in aerospace industry. And another important fact is that all new innovations and technology are generally triggered by the discovery of some new material or some new way of looking at an existing material. For example, if we see the Industrial Revolution, a lot of metals came into prominence in that time, and that led to a lot of industry development. People could manufacture things very easily. New tools could be made. New industrial equipment could be made very easily because of discovery of how to easily make things with metals. So stainless steel and iron, steel, and all these things came into prominence during that time. And various polymers, plastics, which we use today, 50 years back, it would not have been there. And the progress that has brought, that material has brought, is immense. And coming further down, we see composites, advent of composites in the middle 20th century, late 20th century, has been revolutionary in many places. The same way, carbon nanoparticles, nanotubes, nanostructures, nanopowders, all these have been game changing in many different industries. And also, if we see the computer era, the computer era came when they found silicon diodes, and when they found that they could reduce the size of different big integrated chips into smaller ones. So that also was possible only because of the discovery of materials and processing. And so, what is so different in aerospace materials, which makes them uh, a level above other materials, other requirements of other industry? So, the necessary properties of aerospace materials, if we see them, the first thing would be low weight. So, we never want a bulky object to be flying in space, because to make it fly, we need to supply it more lift or propulsion, and that again leads to more money being put in. So the cost increases rapidly. Uh, and at the same time, we cannot compromise on strength or stiffness or any other material mechanical property. So these aerospace materials should have a high strength to weight ratio. That is, they should have high strength at a low weight, which is generally in metals, we don't get that idea. If we have a bigger metal, thicker structure, we think it will have more strength. But aerospace industry needs that. We need materials of high strength and low weight. And the other important parameter in aerospace materials is fatigue resistance, fatigue and damage resistance. So an aircraft or a spacecraft, when it is on the ground, it has no other stresses or no other loads on it other than gravity, the gravitational force on it. So the stresses are very low. But when it is flying in the air, through the air, it experiences a large aerodynamic force, it experiences drag, it experiences many kinds of extra loads and forces which are very high. So this fluctuates. When it's on the ground, it has low stresses. When it is flying or in operation, it has very high stresses. So this fluctuating cyclic load causes something called fatigue. And fatigue is a very dangerous thing because it develops with time. So it may be a small crack at some time which is not visible, but suddenly when it exceeds the fatigue stress, it can catastrophically fail. The structure can catastrophically fail, which is very, very bad in aerospace industry. So materials which are fatigue and damage resistant are the requirement in aerospace industry. And ease of manufacturing and availability of raw material are very important for commercial flight applications. For military applications and space applications, it may not be a problem, but for commercial flight applications or for any other application like maybe drones or some other yeah, unmanned aerial vehicles, the ease of manufacturing and availability of raw material are very important. Another important factor in aerospace materials is repairability. So if a small panel or something is damaged, we that should not hinder, that should not cause us to replace an entire body or structure or part of the aircraft. So these materials should be easily repairable. So if there's a defect, it should be easily repairable and it can go back into operation. There are other special properties. So it can be heat resistance. So some materials which are used in the hot areas of engines, it needs to be very resistant to very high temperature. And also, if you see a spacecraft, so these spacecraft, when they come back from space, they are going to be hurtling towards the earth at a very high velocity, very, very high velocity. So then there's again friction and heat generation. So heat resistant materials, tiles need to be are very important in aerospace industry. Another property, which special property which may be required in certain applications, may be electrical conductivity or insulation as is required. So when we see the evolution of aerospace materials, so when we see the first flights towards maybe the 19th 19th century, late 19th century, so these were basically gliders and all. They were not powered flight. So these flights, and also towards the beginning of the 20th century, all the aircraft, especially aircraft, were made of wood or other a small amount of metals. So when we see the first powered flight in human history in 1903 by the Wright brothers, so that was made basically with wood with some other reinforcing material. And after that, even till the world wars, that is the mid 20th century, wood was still used. There are fighter planes during the world wars which are made completely of wood. But then, due to industrial development, we stepped into metals. So mainly the main metal which was found to be light as well as comparatively cheap compared to other metals was aluminium. So aluminium and magnesium and even titanium in some applications began to be used during the world wars. And coming to the second half of the 20th century, commercial flights took up, and space applications. People uh, started sending spacecrafts, rockets into space, missiles, and many other things started coming up. And for this, they needed very strong materials, and metals could not withstand that much temperature or that much load. So metal alloys, titanium alloys, aluminum alloys came to be used after that. This led to the discovery of a very important class of materials called composites. So today, most of the talk will encompass composites and not much of metals. So I would like to take a small diversion from the history part and come into a small definition of composites. I think most of you would have heard about composites in one way or the other, especially those who are in the second year, third year, or fourth year of your UG or PG. So composites are nothing but material systems which consist of two or more individual constituents, which are put together and combined physically, not chemically. That is an important point to be noted here. And this is done in order to get a resultant or a resultant system which is better than the individual constituents. So the alloys, you may ask, then what is the difference between alloys and composites? Alloys are usually metal based compounds which are combined in a micro level or even a lower level. So when we see it at a macro scale or when you see with the naked eye, it just seems like a homogeneous material. For example, brass or some aluminum alloys. But composites, on the other hand, are macroscopically heterogeneous. That is, when we look at it with the naked eye, or if you cut a cross section of it, you can physically see the different constituents. So the constituents don't chemically react completely with each other and form a different phase. So the two or more individual constituents are in different phases in composite materials. So compared to metals, what are the advantages of composites? Composites are easily tailorable. That is, you can change these constituents to in some way or the other in their structure or the way they are put together or the proportion of the different constituents to give different properties that we need. And also another advantage is that in general composites are lower in weight compared to metals. In general, there are some alloys which are very light, but in general, compared to metals and metal alloys, composites have a lower weight. A possible disadvantage of composites compared to metals is it is difficult to analyze, not experimentally, but it's difficult to analyze it, say with analytical models or numerical simulations, because it has more constituents put together and it is not homogeneous. So it requires a bit of mathematics, a lot of analytical models, difficult models in order to explain composites and in order to understand their behavior without doing experiments. But in recent years, there is a lot of research being done on the numerical simulation of composites. So coming back to some trends in history. So in this slide, what I want you to notice is the proportions on the right of aluminium and other metals compared with composites. So in around 1967, when passenger flights took prominence, the Boeing 737 had around 81% of aluminum by weight in its structure and just 3% of composites and some other metals. When we fast forward to 1991, the Airbus 340 it had developed in its composite proportion, but aluminum still was the major component. When we come down to 2005, again composites around 25% and aluminum around 61%. So composites were being researched on and they were coming into prominence. But when we see in 2009, which is just a 4-year difference from the Airbus A380, Boeing in its 787, it had 50% of composite by weight and just 20% of aluminum and other metals and other materials put together. So this was a rapid change in the passenger or the commercial flight industry. And when we see in a similar fashion, military aircraft also, in 1981, the F-18 Hornet had around 51% of aluminum and just 9% of composite. When we fast forward to 1997, we see that composites are 35%, titanium is 33%, and aluminum is just 11%. So this is a drastic change. This is a drastic change, and it brought forward the advantages of using composites in aerospace industry. So now we are seeing the history of materials and what are the materials which are used. So I would like to just take a small one slide look at stresses in materials. So when we see different materials, say steel compared with rubber, so we see a lot of differences in it, right? So if you take a bar of steel and if you try to press it, it's hardly going to deform. It's hardly going to be it's just like a rigid material. But when you take a rubber piece, say an eraser or anything, and when we just apply a small force to it, it deforms a large amount. There's a large deformation. So we can say that steel is hard and rubber is soft. And another property difference may be that when steel is subjected to very high load, it can deform. It can deform. And when we take out the load, it mostly does not regain its original shape. It's going to stay deformed. But when we see rubber, if we apply a load to it and if we take out the load, it's going to mostly come back to its original shape. So why does steel react differently to rubber? So what is the difference? So the difference is that when we apply a loading or when you apply a deformation to a material, each point in the structure reacts to the loading. And this reaction is called stress. So stress is nothing but a reaction to the applied loading. It may be an external loading, internal loading, or many other types of loading are there. So stresses are nothing but reactions of the material to a particular external or internal loading. So there are different types of stresses as we can see here. So the first figure on the right shows a tensile stress, which is something like an expansion. So if a point in a material experiences tensile stress, that means the point is being that small infinitesimal portion of the material is being pulled apart. Again, we have compressive stresses which compress the material. We have shear stresses. We have bending which causes flexural stresses. So that's the middle diagram here of a beam or a bar bending. And we can in this we can see that the top half experiences compressive stresses and the bottom half experiences tensile stresses. So this is a combined tensile and compressive loading. We also have twisting or torsion, uh, which again causes some kind of a shear in a plane of a bar or a beam. We can also have thermal stresses. Thermal stresses are caused due to high temperatures, temperature differences between different parts of the structure, and they also cause some kind of stress or reaction in the material. And in most aerospace applications or any application, these stresses don't appear individually. Like there's not usually in general random loading, you won't have like tensile stresses alone or compressive stresses alone. Some parts of the structure may have a tensile stress, some may have a compressive stress or a shear stress. So most of the times these stresses are combined in one way or the other, and so that makes it more difficult to analyze and difficult to find out what is the exact reaction of the material. So with this, I would like to just move towards the second part of my talk today, which is about researching in aerospace structures. So This will mostly be my experience in the last 6 years in IIT Madras doing my integrated PhD program. And when I went from UG to the integrated PhD program, my knowledge of research was not that high, of high level research. So I'll just tell you the steps that I took in order to improve my research capabilities, and I'll also go through my research work in brief to show you how to approach a problem, how to select a problem, approach a problem, and how to solve and get results from it. So this is not an ordered list, this research methodology. It is just some important points to note when stepping into research. So the first thing that we do when stepping into research is to select an area of research. It may be a broad area of research. For example, in my case, it's going to be composites. So when I stepped into my integrated PhD, the topic or the area which was given to me was composites, which is a very wide range of topics under it. And the first thing you do is not to directly start an experiment or directly do something, but is to read papers on relevant topics under that broad area of research to know what interests you and to know the current trend in that area of research. The next thing would be to select a problem. So from the papers that you have read, you may think that this particular thing can be researched further. There is a research gap in this particular topic or this particular area of research. So in my case, the problem which I had selected was the improvement of impact resistant structures. So composites are good in impact resistance, but my aim was to find ways to improve the impact resistance of certain composite structures. The next thing would be to select a material which will help solving the problem. So from this point onwards, I will explain in the next few slides with examples how I selected a material and carried out the different steps in research. So after selecting a material which will help you in solving that particular problem, you will have to find out methods to analyze the problem. So it can be an experimental setup, experimental analysis. It can be using analytical models, or it can be using numerical simulations. And after carrying out the experiments, we will have to take the results, compare it with existing or similar experiments or models or some kind of literature, and then we extract what is the new and useful data in whatever results that we have obtained. And then the last step would be to publish the findings as a journal or conference paper. So my broad area of research was composite material. So as I've already introduced composite materials, their constituents can be broken down into two major parts. So the first thing is the matrix. So the matrix is what gives shape to the composite material. So it is a base which gives shape and structure to the composite material, and it also holds the other constituents together. So without the matrix, the other constants will just fall apart. So it holds the other constants together, and when you apply a loading, it transfers the load equally to all the reinforcement or the additives which are added to the composite material. The second, the second part of the constituents, or the second part will be the reinforcement. So I prefer to call it additive because reinforcement means that it's mainly strength reinforcement. When we say additive, it can mean not always strength. It can mean something which is added to the matrix, which improves a particular property of the matrix. It can be strength, it can be electrical conductivity, it can be maybe it can even be to make it opaque or transparent or something like that. So that whatever is added to improve a particular property of the matrix is called the additive. So in nature, there are many naturally occurring composite materials around us, in us actually. So when we see nature, we can see things like wood. So wood is nothing but it's two components put together. It has cellulose, which is a polymer, and which is an additive in this case, and it is present in something called lignin. So lignin is a matrix which holds the cellulose together. So by itself, cellulose, when we extract it, it's something like simply a powder or something like that. But when it is held together by lignin, which is a matrix, it gives wood, and you know how strong wood is. And in our own body, bone. So bone is a combination of collagen, which is soft and flexible, and hydroxyapatite, which is hard and brittle. So individually, these two are almost like they don't have strength, but when they come together, they produce something as hard and as tough as bone. So this is in nature itself, we can see composite materials everywhere. And we have also, as humans, we have always replicated nature. So we have also tried making composite materials on our own. And again, composites in this way can be classified into many types. There are many types. This is not an exhaustive list. This is just some of the more important composites which I have noted down here. So based on the matrix, we can have polymer matrix composites, ceramic matrix composites, metal matrix composites. Polymer matrix composites are very widely studied and used in structural applications. Metal matrix and ceramic matrix composites are used in special applications. And based on the additive, we can have to the matrix, we can add fibers. So fibers are nothing but long, thin strands of any material. It may be glass, carbon, it can be some polymers which are drawn into very fine strands. And we also have natural fibers like jute, hemp. So all these are form fiber reinforced composites. We can also have particle reinforced composites. So particle reinforced composites can be something like rubber, which is toughened by adding some tougher particles, some ceramics or something like that. So particle reinforced composites are also widely used. Nano composites are coming into the forefront in the recent years because of their electrical conductivity, because of their high strength. So nano composites, which are matrix to which some kind of nanoparticles have been added, are also being used in the composite industry as of now. So composites is the general area of study which I chose. And then my problem was based on impact of structures. So a little bit about impact. So as you know, impact is nothing but any loading which takes place in a very short interval of time. It can be a few microseconds or even less than that. And there's a huge load uh, which is acting on the material in a very, very short time. So this can be of many types. It can be due to crashes, car crashes, or any other crashes of two or more huge materials. And it can also be due to blast waves. So blast waves are similar to crashes, but in crashes physically two bodies are hitting each other, while in blasts what happens is the shock waves from the blast hit some impinge on some structure and damage it. We also have ballistic impact. So ballistic impact is nothing but a very small sized object hitting another body at a very high velocity. So it can be something like a bullet hit, or if we think about satellites in space which are moving at thousands of kilometers per hour, it can be some debris, some space debris, or some particles in space hitting these satellites. So the particles may be of same some millimeters in size. It can be like dust, but when it impacts the satellites at a very high velocity, hypervelocity, it can cause extensive damage. So these kinds of low mass, high velocity impact are called ballistic impact. You can also have low velocity impact, like a tool drop. Even a tool drop in a composite material can be dangerous because it can cause defects inside the material which are not visible to the outer naked eye. But when such a material which has been damaged by a tool drop or some very low velocity impact undergoes fatigue or any other high kind of loading, it can cause extensive and premature damage in the material. So impact resistant structures. So what are impact resistant structures? They are structures which protect an important payload from impact loads. So these are something like a protection layer around something important. So the important payload may be human beings in aircraft, or it can be some satellite which is being taken into space by some rocket or other spacecraft. The principle behind impact resistant structures is to absorb as much as the impacting energy as possible. So these are also called energy absorbers. They absorb the incoming kinetic energy and prevent that energy from reaching whatever is being protected inside. And I was looking at a specific type of energy absorbers called sacrificial energy absorbers. So these are energy absorbers which come into action very rarely when these high impacts happen, and they themselves fail, but they protect the payload which is inside. So as you can see in the image, there is a car. So the car bumper can be an impact resistant structure. It is an energy absorber because in the event of a crash, this bumper, it deforms, or through some mechanism it absorbs all the energy and it protects the passengers inside from any kind of physical harm. So car bumpers are a example of crash resistant structures. You can also have for ballistic impact, to protect military personnel from bullet impact. We can also have protective jackets. We can also have protective jackets which protect an individual from shrapnel, from some kind of debris from blast or from direct bullet hits. So these are some examples of impact resistant structures, sacrificial impact resistant structures. These sacrificial energy absorbers, once they are used, they cannot be used again. They just fail, but they protect the payload, which is the more important part. So while researching into these, we came across a particular material system called syntactic foams. So syntactic foams are nothing but they have a matrix, which can be polymer, metal, or any other matrix, in which we add some hollow particles or any other fillers or additives which aid in fabricating low density composites. So as you can see in this image, the structure of a syntactic foam, there is a matrix in which we add hollow particles. So inside this hollow particles, there are voids or intentional voids. But then these particles are strong enough. So these are not like just some sponge or something, but they are reinforced voids, which reduce the density and weight of the material extensively, at the same time giving considerable strength. So on the right side, we can see the scanning electron microscope image of the hollow particle that we have used, which are glass microballoons. So the matrix that we have used is a polymer matrix called epoxy, which is a commercially available polymer matrix, and we have used glass microballoons to act as the hollow particles to create these syntactic foams and to study them in impact resistant structures. So I will just tell in brief about two main works that I did in my PhD. So the first type of impact that we studied was crashes or blasts. So the crash worthiness of composite tubes was what we initially studied. So in this, the structure is a composite tube which is being subjected to a loading, that is longitudinal crushing. So in a longitudinal axis, we are going to be studying the crushing of these tubes, and the aim is to improve the crash worthiness. So crash worthiness is nothing but if a car is coming into market, they test whether it is worthy of withstanding some kind of crash or some kind of energy impact on it. So to improve the crash worthiness or the energy absorption characteristics of these composite tubes was the first work that we did, and it was published in Thin Wall Structures, a journal. And what we did was we fabricated these composite tubes. So in these composite tubes, we made it using glass fiber and epoxy matrix, which is a normal GFRP composite, as they call it. And we made tubes. And instead of just using epoxy as a matrix, we used these syntactic foams as a matrix. So we added glass microballoons along with epoxy in these tubes, and so they stay hollow. They don't get filled inside; they stay hollow, but They're filled within themselves with these glass microballoons, and then we subjected them to crushing loads, to compression. So on compression, we found it is already found that when tubes compress, they fail in a progressive manner. They don't fail catastrophically. If you take a bar of composite, especially composite, and compress it, it's going to shear off and it's going to fail catastrophically. And there's no warning or anything. It's just going to break off at an instant. But when we compress these tubes, it gives rise to this petal kind of formations. So these walls are split and they bend inwards and outwards, and they give a kind of petal formation, which aids in progressive failure. So when you deform something progressively, you're doing it for a long time. You're elongating the time of the compression, and this leads to higher energy absorption. So I have a video of this one. I don't know how nicely it will stream on the YouTube channel link, but I'll just play this, and if it plays properly, you will be able to see the bottom plate compressing this tube, and you can see these petals which are formed. These petals which are formed, and then they break off after some time. So when you go back to this, you can see that the top end is chamfered, or you can see that it's smoothened in one way. So if we do not do this, it again leads to a kind of catastrophic failure. So this chamfering initiates the petal formation, and then you can see it gradually fails until almost the entire length is compressed. And this is the representative and actual load displacement plots which we obtained from our experiments. And we can see that there are three regions in this one. So the initial first region is the region where the chamfered region is the chamfered part of the tube is compressed. So it's almost like a linear elastic material, like any other material would start to deform. But the second region is what is important in these progressive failure based structures. So in the second region, we can see that there is a lot of undulation and up and down movement in the load displacement graph, and it extends for a long time. So it's like a plateau, flat plateau region in which the load undulates at a mean load. So the mean load is almost constant in this one. So this mean load is called the mean crush load. This load, and then after the entire tube has been crushed and it behaves again as a solid, it again the load again increases. We are not bothered about this third region. We are only bothered about the first region and the second region. So as you can see, when we increase the amount of hollow particles within the matrix from 0% to 30%, we can see that the mean crush load is increasing at each level. So this shows, and also an important point here is that the energy absorbed by the material or the structure is given as the area underneath this load displacement plot. So if you just have a material which withstands a very high load and then breaks suddenly at a very low displacement or deformation, the area under the curve is going to be very low. But on the other hand, if you extend the area under the low displacement plot like this, you get a very high energy absorption. So this is the difference between catastrophic failure and progressively damaged failure. And in addition to the experimental analysis, we also did a bit of analytical studies using an energy-based analytical model. So in this also what we did was quite simple. So if this in the image, you can see that we have shown a cross section of a tube wall, which is on compression is petaling on both the directions, bending on in both the directions, first splitting and bending in both the directions. So we can analyze this as initially there is no splitting or no bending, and when the crushing plate compresses the material or the structure, it's going to split, bend, and create these petals, and at one point or the other these petals are going to just break off or get damaged beyond any load carrying capacity. So there's going to be a compression, bending, and then the petals break off, and then this cycle will repeat again and again. This is what causes the undulations like this. So the undulations are almost of the same displacement. So each cycle length is called is denoted as h here. It is called a single crush length. So at each crush length, we can calculate the external work done, and also we can calculate the different energy modes of energy absorption or energy dissipation. So because of delamination, there may be some energy which is absorbed. Because of axial cracking is nothing but these cracks, these axial cracks which are formed uh, in the longitudinal direction. So because of this cracking, there is some energy that is absorbed, and due to petal bending and interlaminar shear in the petals, and also due to friction between the crushing plate and this composite. So because of all these things, there is some energy which is some amount of energy which is absorbed for each crush cycle, for each crush length. So what we can do is we can equate the input energy, that is the external work done, with the sum of all these energy absorption terms, and then by rearranging these terms in a proper way and simplifying the equation, we can find the mean load, which is which the structure experiences during one particular crush cycle. So this is the same as the mean crush load in this plateau region. So by using analytical model, energy-based model, we can find out the mean crush load, and also we can subsequently find out the energy absorbed by the structure analytically without actually performing the compression test. For to get these basic mechanical properties, we take a normal composite plate made of the same material, and we test it for the normal mechanical loading such as tensile loading, flexural, shear, as well as fracture toughness. So these are the different parameters which we have found from experiments, and when you plug it into this equation, we can get the mean crush load and energy absorbed by the structure. So for different materials, this terms are going to be different, and the mean crush load is going to be different. So these are some of the results that we have published. So this first table shows the numerics involved. So as we see, when we increase the volume fraction of the glass microballoons or the hollow particles, the density decreases rapidly from around 1.6 gram per centimeter cube to 1.2 grams per centimeter cube. The mean crush load, as we saw earlier in the graph, increases from around 8.87 kilonewton to 14 kilonewton. Because these densities are different, to compare these materials of different densities, we have a term called specific energy absorbed. So the specific property, as we saw, was the property itself divided by either the density or the weight of the structure. So in this case, we have divided the energy absorbed by the weight of the structure, and we find an increase in the energy absorbed. So when we see the experimental and analytical comparison, we see that the analytical values are almost comparable to the experimental values. And an application, the application of these tubes can be to mitigate blast effect on important structures such as bunkers, such as some important chambers. We can use these tubes, which are longitudinally placed in this fashion in a pattern, and then we have a plate above it. So now when the blast waves, the blast pressure hits the structure, these tubes are going to fail and absorb all the energy, and they protect the important payload or structure underneath. This can also be extended to a car bumper system, where if you place this in front of the car or on the side of the car, any impact on any impact, these tubes are going to absorb all the energy and protect the passengers and other payload inside the vehicle. So this was about the crashworthiness of composite structures, in particular composite tubes. Another small, another brief thing that I would like to say is the second part of our research, which is the ballistic impact of sandwich panels. So in this, what we did is we tested some sandwich panels containing the core material, which is made up of these syntactic foams, and the skin, which is made up of normal GFRP or glass fiber reinforced polymer composites. So the skin had glass fibers and epoxy, bidirectional glass fibers and commercially available epoxy, while the core was made of epoxy and hollow glass particles, as we saw earlier. And in the manufacturing of this, so in this case also we wanted to increase the energy absorption of this particular combination or this particular structure. So what we did is, in our case, both the core and the skin are composed of the same matrix, which is epoxy. And this is a nice thing because we can co-cure this one. So it's not like we make the skin separately, the core separately, and then join them together using an adhesive. But on the other hand, we make the bottom layer, we wait for some time till it gels, we make the core, and then before the core gels or cures completely, we make the top skin. So it's a co-cured method in which the entire composite cures at the same time, and so we were hoping to increase the energy absorption of this material. And this is the setup that we use, the flexural setup, which is a 3-point bending setup in which there are 2 supporting pins and 1 pin which applies the load and causes the bending. And this is the ballistic impact setup which we had used, in which we can see a similar sandwich plate, which is held in place to a rectangular frame using C clamps. And this in the middle is the metal projectile that we used to impact these sandwich plates and to find out how they behaved. So again, here's a video of the composite plate being impacted by a projectile on the left. So this left barrel is from a gas gun which we have in our laboratory, which can fire projectiles from anywhere from 50 meter per second up to around 300 to 400 meter per second or even more. And actually, you cannot see the sandwich plate, but it is here in between these 2 rectangular frames. And so when we see the projectile approaches the sandwich plate at a velocity, some of the energy gets absorbed by the plate, and in this case, it has penetrated through the plate completely and goes out with a reduced velocity. In some cases, if the plate is strong enough, it can cause rebounding of the projectile also. I'm not going to go into the numeric results of this one, just a graphical result page here. And this is the result of the flexural test that we did. So if we have the skin and core separate, made of separate materials and then put them together, one of the major failure modes which was seen was skin core debonding. And this happened initially itself, but because of the co-curing method, we have delayed the skin core debonding, which causes complete failure. And so in our case, what happened is we had core cracking first, and then fiber failure, and then we had skin core debonding. So this again, as we saw in the load displacement graph, increased the area under the load displacement graph and caused a higher energy absorption capacity for this particular co-cured composite. And for the sandwich panels also, we had a lot of numerical results, which I'm not going to discuss here. And this is just a CT scan of different sections of a sandwich panel after the impact of the projectile, complete penetration of the projectile. So in A and B, we see the front skin, and we can see the impacted area in which the projectile has penetrated. And the syntactic foam is just matrix and hollow particles, which is a brittle material. So you can see a brittle failure here where this entire area has failed. And again, this E is actually the back skin of the material, through which we can see that the projectile has completely penetrated and caused kind of a petal formation here. So yeah, so this was about how I approached my research and how I chose a broad area and then narrowed it down to a particular problem, and how we went about in solving different things in the problem, and how we improved the material in some way so that we could get a higher energy absorption capacity in the material in different structures, in tubes as well as sandwich plates. So for those of you who are in your undergraduate third year, fourth year, or even earlier than that, possible areas for research, possible avenues or possible ways, steps you can take for research in structures, in aerospace structures are, you can look into the behavior of new materials. So the materials can be new. You can take a base material and you can add some new material, or you can change the composition, or you can change some property of a material, like heat it for a longer time and then add it, or some kind of difference in the material or the manufacturing process. And you can use existing test methods and you can analyze these materials either experimentally, or you can do it analytically also. Some examples in current research trends are shape memory polymers, which are widely being analyzed. Even in our lab, we have research being done in shape memory polymers, and these are used for things like automatically shape changing wings of aircraft and spacecraft. So we need not have separate control surfaces. The entire wing can be can change its shape as required and on application of certain external stimuli. And you can read more about it if you want. Shape memory polymers are an interesting area of research. Modified composites, like what I have done here, modify the composites, the method of fabrication, and find out better applications of the same materials. And also you can try hybrid composites, in which two or more different fibers or different particles are put together to get a better composite. You can also analyze newer structures for certain applications. This is more of design. So for this, we can analyze. We can think about something like analysis of complex structures using some kind of a software, numerical software, or you can use analytical models, and you can analyze some new structures, new design, new models for existing applications. And also the third thing is that you can develop new methods or setup. So there is, for most of the things, there are already predefined setup. Like for a tensile, if you want to get the tensile strength, you have a certain standard, ASTM standard, you follow it and you do the test. But for some kind of properties, like the out of plane shear strength of materials, or some complex loadings, some complex fatigue analysis, there are no proper methods as of now, no proper standards. So you can also work in development of new standards or new setup, even new setup, an advanced setup for analyzing existing materials. So these are some possible avenues for research for people who are just starting into your aerospace career. And yeah, you can do this not only as an academic thing after UG, even while doing your UG, you can just look into some things. And the most important thing is reading papers. So reading more journal papers and getting ideas and staying in touch with current trends is what is needed for research, and then seeing what you can do, what more you can do from there. So yeah, that brings me to the end of my talk, and my acknowledgements to the head of my lab and my PhD guide, Professor R. Velmurugan, in whose guidance I have done all this research. And so Professor R. Velmurugan is a senior professor in Department of Aerospace Composite Lab, IIT Madras, which is very near for those of you who are in JPR or in Chennai. And in our lab, we do various things like, as I said, fabrication of composite plates, tubes, and other structures, mechanical testing of these composites, normal static testing, as well as fatigue testing. We have testing machines from 5 kilonewton to 100 kilonewton capacity. We also do thermal analysis of composites polymers, such as digital scanning, calorimetry, and we have a dynamic mechanical analyzer, some thermal analysis of composites. We are specialized in impact testing machines. Like I said, we have a gas gun which can fire projectiles currently up to 400 450 meter per second, and it's expected to develop in the future. And we also do a lot of analytical and numerical analysis on composites, which combined with the experiments makes a complete and whole package. So thank you for your time. Thank you for the opportunity given to me by JPR Engineering College, by Professor Haston, the HOD Professor Tanigavel, and others in the department and the college. If you have any doubts, you can contact me at my mail ID, which is danielpaul.imrs@gmail.com. And also, you can find the research of our lab in LinkedIn, ResearchGate, Google Scholar, and other sites. Thank you.
Thank you very much, Daniel. That was really insightful, especially you touched all the fundamentals. You have spoken about your research work. That was really nice to see.
Sir.
You worked hard. There are a few questions in the chat actually.
Yes, sir.
There are a few general questions and there are a few technical questions.
Okay, sir.
I would like to ask, first general question was, in which part of aircraft composites are mostly used? Fuselage or wings?
So again, that depends on, because there's a large variety of composites which are available now. So polymer composites are generally used in areas where there's not a lot of high temperature. So something like the fuselage. The fuselage is currently, as far as I know, Boeing and Airbus, they make fuselage out of a single run of something like it's called a filament winding technique. So they take fibers and they wind it around an entire mandrel to make the entire fuselage in one go. So the fuselage is made of polymer composites nowadays. And also in high temperature areas of the engine, we use metal matrix composites. So instead of polymers as the matrix, we can have metals like aluminum or titanium as the base material. And these are used in high temperature parts also. So basically, composites are being used all throughout the aircraft in different areas. Only some areas are not replaced completely by composites in the current trend.
And there was another question, Daniel. Why can't the titanium material be replaced instead of composite material? I know it is an easy question. Why we are not using titanium instead of composite?
Yeah, titanium is costly. It's very, very costly. So most of common applications, for space applications, of course, they use titanium. They use very costly materials. But for commercial flight applications and normal applications, they do not use titanium much, except in very high critical areas.
There was another question. How to test a material to know its fatigue strength?
Yeah, so fatigue, it again has its own standards. So fatigue testing is very common. And what we do is we apply a cyclic loading. We apply either a tensile compressive loading or a tensile loading. And we let these cycles happen for hours and days together for lakhs of cycles. And then for every material, there is a particular standard which limits the number of cycles before which it should not fail. So if it fails, then it fails the test. So fatigue machines are available widely, even in our lab it's available. So it's basically cyclic loading. It's similar to static tensile or compressive loading, but it happens again over and over again. It just loops over. So that is basically a fatigue test.
So we spoke about impact. So in case of hailstone,
Yes.
how an aircraft body can resist this impact in case of composites?
Yeah, so hailstorm is again, as we saw, it may fall under something like a ballistic impact. So again, having a very so these composites are not may not always be used only composites. So it can be different layers. So you can have a stronger a metal maybe a metal layer also outside with along with the composite. But generally, hailstorm obviously you cannot prevent it in any way. So again, it depends on making the composite strong enough, giving a proper factor of safety, so that even if some damage happens, it's not going to destroy uh, the entire part or entire structure cross section. But it can take it. For example, you can have some energy absorbing layer also in between. That is a very important, useful thing that you can do.
Another question, Daniel. What are the other catastrophic failures that can occur when we use
So
composite materials?
yeah, so composite materials have different, have many damage modes, which is one of its disadvantages. So it can fail by the fiber failing, it can fail by matrix cracking, by interlaminar shear, it can fail by fatigue loading, it can fail by fracture. So yeah, so it has a wide host of failure methods. But the advantage of composite is that even if one fiber fails, the rest of the structure can still take the load. So yeah, so there are the modes of failure in composites are very large. Uh, yeah, so you can look into that.
Another question. What are the softwares used for analytical and numerical work? Is the mechanical workbench of ANSYS commonly used?
Yeah, so ANSYS Workbench is one of the most commonly used structural things, structural software. But currently, there are many other softwares which are coming into play. For example, LS-DYNA. LS-DYNA is a software used for dynamic analysis. We have Abacus. Abacus is again used for static and also for fatigue applications. And these are all commercial software for which you will have to pay and get it. So even yesterday, as I was listening to the talk, Professor Kanan was saying about these open source softwares. So there are a lot of open source codes which are available, in which you can yourself code the entire, maybe the model itself. In ANSYS or Abacus, you don't know what is happening behind the scenes. You just plug in a diagram, which is the structure, you apply the loads, and you just get some results. You don't know what is happening behind. So if you're interested in analytical modeling, you yourself can use some basic language like C++, or there are many other languages. There are also open source softwares which aid in which have packages, FEM packages, mainly finite element method packages, which you can use in order to analyze these problems.
So you have all this inadvertently suggested what softwares students should learn before going to research. So that was so
Yeah,
smart.
it's a wide range, and whatever is comfortable for us, we can use it.
Uh, there is another simple question. What is the difference between aluminum alloy and aluminum alloy composite?
Yeah, so yeah, aluminum alloy is basically, as I said, it's a homogeneous mixture of aluminum with some other materials. Composites are like you combine it with other metals or with some fiber composite or some other composite, you get an like it's a combination of aluminum. So if you would have seen in my slide, there was a thing called GLARE, GLARE. So that is glass fiber composite which have been laminated along with aluminum composite. So that is one kind of metal polymer composite.
So another personal question. Uh, we would like to know how was your research experience and what are the challenges you faced during your research?
Yeah, so challenges faced in research are vary from people to people. So some the main challenge would be to understand the guide and to understand the problem basically. So if you have a problem, if you have a research area, and the first challenge will be to formulate a problem. So in my case, I took impact analysis as the problem, and then I developed it from there. So to find out what we are doing is the first step. So if you do a theory-based program like BE or BTech or MTech, you are told what to do. You are told what to do. You are given the syllabus, and this is what you learn, and this is the exam, and that is it. But in research, it's more flexible. In research, you yourself have to formulate the problems. Like you write the questions and you answer it. So you need to first know how to formulate the problems, and then you need to have enough skill and enough resources to solve that problem and to bring out some results from it. And yes, there'll be a lot of failures along the way. There'll be a lot of topics which you start, you spend 2 3 months in, and then there's no result. So you'll have to just scrap it and then start from scratch again. So yeah, one of the main challenges in research is that it's very flexible, and there are a lot of things which can go wrong. So you need to be confident enough so that you can try again and again till you get a proper. And also there's no time frame. The time frame is also flexible, so it can go on and on for a long time. So you'll need to know what you're doing, and you need to take proper steps in order to reach that target. And then if time permits, you do more.
One final question, Daniel. Can you suggest any areas of research in composites? If suppose there is any aspirant who wants to do research in composite, so what area, what particular topic, or what particular field you would like to suggest to work on?
So currently, the trend is moving a bit away from experiments into a lot of modeling, a lot of numerical simulations, because they can be done from anywhere. That is the first advantage. So I would ask the students. So mathematics initially seems a bit tough and difficult to understand sometimes, but understanding the mathematical models behind materials, for example, how steel behaves, how rubber behaves, and yeah, to take it from there would be it's in current trend. That is a good thing to do. And also in composites there are a lot of variations which are possible. You can play around with materials, you can play around with the matrix, with the fiber. So that is also for beginners, that is a easy thing to do. Yeah, you come up with a new structure or a new material combination, and you can test it for various mechanical properties, specialized mechanical properties, and get the result. That is a simple experimental thing. And also you can go into more of simulation, Abacus, ANSYS, and other software. So keep simulating some structures, and you come up with new structures, find out how it's behaving. So that can be a beginning of some kind of research.
I think we have come to the end of today's webinar. You have answered all the questions straightforward and very simply and in a very
Yeah.
understandable way. And your presentation was awesome. Thank you so
Thank you.
much, Daniel. So
Okay,
once
thank you.
again, on behalf of Department of Aeronautical Engineering of JEPPIAAR Engineering College, we thank all the participants for attending this webinar. And also a special thanks to Daniel for your valuable time and for presenting a simple uh, understanding. Especially, it is motivating for all the youngsters, those who are just going to graduate, and those who would like to do their project, those who want to start their research. You are given a simple guideline, and which can take them into a very large field. I hope this webinar would have touched many people. And to the participants, I would like to make an announcement. I have sent the feedback link in the chat, and kindly join us back on Thursday. So Thursday we'll be having our webinar on innovations in jet control. We will be having speaker Dr. Dharmendra Singh Chand from Chandigarh University. So we will be having a session from 5 p.m. to 6 p.m. It's not 4 to 5, it will be rather 5 to 6. So we will post you, or we'll keep you updated in the WhatsApp group. Once again, thank you all, and we will meet once again.
Thank you, sir. Thank you, everyone.